As I told you, we finish Friday next week. More or less, I will be trying to finish today the whatever is concerned the physics, and then from Friday we'll have the lectures on oceanographic instrumentations. So this is more or less the plan until the end of our lectures. Shall I close and open a little bit the window or not? Huh? You want it? No. No. So I leave this open.
No.
Close almost there. Everything closed. Okay. The light also. No, that's good. Okay. So far we were discussing mainly from the analytical point of view the steady solutions, the solutions where at the equations of motions we the main assumption is this one, that the changes of the current field with time is zero, so that these are the steady state solutions. And not only that, but also this thing here, ddt, you know the difference between this and this. You know the difference between the two, I don't have to explain to you. So this is the steady state solution, and these steady state solutions are these what we obtain from the equations of motions, and these the two main solutions what we were discussing in very details are the Ekman-Levi solution and the geostrophic flow. The main features of both of these solutions is that they have a large spatial and temporal scales. Temporal scale, they have to be large in order to satisfy the steady state requirement. And they have also the large spatial scale. The large spatial scales are those which helps to, first of all, to neglect the nonlinear terms. Nonlinear terms are the advection terms, which are this thing, for example. These nonlinear terms, and they depend on the length scale. The largest the length scale, it's easy to neglect it. The approximation of neglecting the nonlinear terms is better, functions better. So we have the large temporal and spatial scales, which are helping us to make the assumptions of a steady state solutions, which are those two. The thing is that these two solutions are something which describes pretty well what is happening in the real ocean is another thing. What we have noticed by doing the measurements, and how do we do the measurements? We do the measurements by doing the long-term average, because the long-term average guarantees us this dt equals 0, and so and by doing these type of measurements, we demonstrate rather often, and quite often we demonstrate that these these steady state solutions are good approximation of the real processes in the ocean. We have shown this on large scale oceanic circulation. We have shown on the subtropical or dry as in the world ocean. And now we will mention few time-dependent or wave solutions, where this ddt is different than 0. Okay, so and also here we should. I mean, this is not these solutions. wave solutions are something which is also present and has a signal in the real ocean, and therefore they are very useful in order to understand some phenomena. What we have noticed by measurements. This is what you remember, if you remember last time. This, for example, the equatorial Rossby waves, equatorial Kelvin waves, and which are explained very qualitatively in this way, that where you have the coastal Kelvin waves, which then interfere and meet in the equator, and then progress toward the eastern part of the ocean, and then again separate, one going southward, the other one going northward. This is a very simple explanation of the process, which is of the El Nino phenomena, which appears in the world ocean. So let's see how this looks like in the equations. How this looks like in the equation, what kind of solution, what kind of assumptions we have to take in order to obtain the Kelvin wave solution, Kelvin wave equations. These are the equations which explain the Kelvin wave solution for the coastal Kelvin waves. Let's first look at the physics of the Kelvin waves. These are the inertial gravity waves, and if you have a coast, in the coastal area you have the shelf. The shelf means that you have a slope in the bottom. The bottom is sloped. So that means that you have the coast, and then you have the slope, continental slope. If the particles are moving parallel to the isobats, then nothing is happening really, because the vorticity of the water column doesn't change. Unless if we assume that F is constant. So Kelvin waves are on the F plane. F is equal constant. So if the particle is moving parallel to the coast, the F doesn't change. Doesn't change because the particle is moving north-south in short distances, on the distances on the order of 100 kilometers. The only thing what would happen is that the relative vorticity would change. And how the relative vorticity would change? It would change if the particle, which is the water column which stays here, is moved perpendicular to the isobats. So if it changes the width, the h changes. You remember that we were talking about the theta over h, where theta is the relative vorticity and h is the depth or the height of the water column. And only if the water column moves perpendicular to the isobats, there are changes of the relative vorticity. And so, in order to satisfy the potential vorticity equation, where F in this case is changes of F in this case is 0, theta over h has to be constant. So if the water column moves toward the coast, it will be squeezed, and it will rotate. It will gain the anticyclonic negative vorticity, or vice versa. If there is no forcing in the equation, what would happen? That the particle will try to go back to the previous position where it has the the ambient vorticity, relative vorticity. And then it moves back, but it overpasses the original position and goes to a deeper area. And then there gains the positive vorticity, and then tries to go back to the shallower area, and then goes back and forth. And this is how really the wave-like solution, wave-like oscillation starts, and how the so there should be a first impulse, the first something which forces the water column to move across the isothickness. And this is wind, for example. The wind can, at a certain area, can force the water column to cross the isobats, and then goes toward the coast or from the coast. And this is how this external force then makes the particle, the water column changes the depth, changing the potential vorticity. So this is the explanation of the physical mechanism which makes the water column move. And if you look if you look from upward, then here is the deep, here is shallow, this is the coast. What is happening? The water column here is relatively straight, relatively narrow. Here, if you go toward the deeper area, the water column is become larger. And so here, the water column gains the negative vorticity. Here, the water column gains the positive vorticity. Okay, so both water columns, one which is moved toward the open sea and the other one which is moved toward the coast, have the same velocity in the same direction, which means that the propagation of the Kelvin waves is possible only in one direction. This direction means that the perturbation leaves the coast at its right, at the northern hemisphere. Okay, so by doing these simple considerations, qualitative considerations, we have found out the mechanism what is generating these waves, and on one hand, on the other hand, some features of these waves. Okay. Obviously, these waves cannot appear at where there is the bottom is flat. With a flat bottom, obviously there is no mechanism which changes the height of the water column. Therefore, the main amplitude, the largest amplitude, or the appear of these Kelvin waves appears in the area where there is the bottom slope. If there is no bottom slope, there is no mechanism generating the Kelvin waves. Okay, so these are the qualitative consideration which will then obviously we will try to get by looking at the solutions of the equations of motions, assuming the non-linearity in our equations, and this is the gradient of the free surface, because these are the barotropic Kelvin waves. Barotropics Kelvin waves are those which appear in the vertically homogeneous water column. So these are the equations. We have the coordinate system, which is this one. X is this way, y that way. So this is a typical coordinate system what we use. North is epsilon, north is y, and x is eastward. And then there is a boundary conditions that mean that says that u is equal to 0. So the velocity perpendicular to the coast is equal to 0 by simple boundary conditions. And then the equations before, what we had before, we have this set of equations, the two equations in x and y direction, where effectively in a x direction disappears the u dt. The u dt disappears because u is equal to 0. The velocity perpendicular to the coast is equal to 0. In the y direction, there is no Coriolis term. There is no Coriolis term because u is 0. So this is the very simple set of two equations. And what is important here, if you look at these two equations, it is important that across the isobats, perpendicular to the isobats or cross-shore, the balance is just right. There is a balance between the velocity is a function of the horizontal of the sea level slope. This is very important and essential characteristic of the Kelvin waves. So Kelvin waves are having the velocity parallel to the coast, which is a function of time, and perpendicular to the coast is steady component. So this is something which is very, very interesting, very important characteristic of the Kelvin waves. The solution is this thing, where this is the solution of the sea level. So the sea level 4 is this way. It has perpendicular to the coast is exponentially decaying. It's decaying perpendicular to the coast, and then obviously has this time-dependent cosine function, which shows which satisfies this second component equation. Now this is something which is interesting. The thing is that we have to find out this LD, the distance where there is no signal associated to Kelvin waves. Obviously, since we were talking here about that, we found out that due to the potential vorticity, due to the relative vorticity, to the conservation of the relative vorticity, the Kelvin waves can be concentrated on a continental slope. Therefore, this LD, this coefficient has to do something, has to be the function of something which describes the depth and so forth. Let's see how it looks like. Okay, so this is what we said right before. The amplitude decays offshore with a scale equal to the deformation radius. Okay, now we introduce something which is called the Rossby radius of deformation, which is this one here. We obtain from the equations from the boundary conditions, we obtain that the time scale on which the amplitude of Kelvin waves decays and goes to 0 is the typical time scale is square root of GH over F. If you do the dimensional analysis, you can see that this really has the dimension of L, where G is the gravity, acceleration of gravity, H the depth, and F is the Coriolis parameter. And this is this is called the Rossby radius of deformation, external Rossby radius of deformation, because it's associated to the barotropic flow. If you want to understand what is the distance, typical distance where we don't see or don't feel the Kelvin waves, we can simply put here the typical numbers, what we what we have, like the typical number for G. G is 10. H, if we put H 100 meters, so we have a square root of 1,000 divided by 10 to the minus 5. Okay, so square root of 1,000 is 30, right? Something like 30. 30 times 10 to the 5 meters, 10 to the 5 meters, so it's like 100 or the order of 100 kilometers. So the Kelvin waves are trapped in the coastal area, trapped in the coastal area in an area which is wide about 100 meters, 100 kilometers. Sorry. So we call this that the waves are trapped to the boundary. That means that they don't leave the boundary. They always stay in the at the boundary, and they travel at the northern hemisphere, leaving the boundary on their right. This is the dispersion relationship, which shows simply that for the H constant, the frequency is a linear function. It's linear. So these are the characteristics of the Kelvin waves. If you want to observe the Kelvin waves, what we will do? What kind of measurements we will do? What kind of measurements we will do? Sea level, for example. If you want to observe the Kelvin waves, we should do the measurements along the coast. And the signal first, obviously, will be first recorded at the southward station, and then later on with northward station, because they are progressing that way, right, in the northern hemisphere. We have another, as I mentioned you before, and we showed this in a qualitative way. We have also equatorial Kelvin waves, where we have which are due to the changes of the sign of F passing over the equator. So there is no changes in absolute terms, but it's only changes in the sign, and essentially the mechanism is very similar, because if you have the equator, and if the particle which is staying in the northern hemisphere passes down here as far as its relative vorticity, it should be enlarged, so it gains the negative vorticity, and vice versa. So it will oscillate around the equator back and forth in order to arrive always at the to be at the position where its vorticity is equal to the ambient vorticity. And so this is the mechanism which makes this equatorial Kelvin waves generating. And so they have a Gaussian type shape, symmetric about the equator, and this is the solution. Okay, this is the sea surface, which is function of x and time. Okay, where we have in the y direction, so that means north-south direction, it is the exponential function of this thing. So decays both northward and southward exponentially, and here we have again the time-dependent part is cosine. In this case, however, the length scale, or the typical length scale, where we have this decadal reduction of the of the sea level, it's this is a length scale. So the length scale is here we have G prime H1 over 2 beta. Here, instead of G, we have introduced something what is called G prime. This is a reduced gravity, because here we work with a vertically stratified or two-layer fluid. Two-layer fluid means that the reduced gravity is proportional to the difference between the upper and lower layer differences in the difference between the lower and upper layer density. And so here, instead of F, we have beta. Beta is, if you remember, beta is the north-south gradient of Coriolis parameter, which is this thing here. And so this is the, if you look at this term here, you will see that the rho minus rho prime divided by rho is not is on the order of we have differences in density of 1% between on the order of 1% between lower and upper layer. So that means that this is here is 0.01. This is an error because it has to be a rho. It has to be G here to make mixes G here, because we multiply G by this thing here. And so we have here instead, before we had, if you remember, we had the G is 10, but here is, this is 1% divided by 1,000. So we are we have a G divided by 1,000 is practically the reduced gravity value, which is 0.01. So that means that the length scale is smaller here. Obviously depends on beta, to what is the rate of change of beta going north and south. Anyhow, in this case, if we talk about the equatorial Kelvin waves, we are talking about the waves which are trapped along the equator, not anymore along the coast, but along the equator. Okay, so we have equatorial Kelvin waves and we have a coastal Kelvin waves. Here we have this. Here we have the internal radius of the formation is around 200 kilometers, while the Kelvin wave speed is around 2 meters per second. It's pretty high speed if you think, if you think in terms of the wind speed. We have 10 meters per second is the, so it's quite almost at the order of the wind speed. These waves, very fast waves, but very long. They have wavelengths on the orders of hundreds of kilometers. And this is how we explain the arrival of the signal from west to east, which is due to the Kelvin wave. So the Kelvin waves are taking the signal which is happening at the western coast of the Pacific and brings them to the eastern coast. And this is what is the very schematic presentation what we have seen here, where we have a combination of the equatorial or of the coastal and equatorial Kelvin waves. These are coastal Kelvin waves which then meet at the equator and progress toward the eastern coast of the Pacific, and then again separate in two coastal Kelvin waves, one going northward and the other one going southward. and they go in the opposite direction because there's a change of the Coriolis parameter. So in the northern hemisphere, they leave the coast on their right, or leave the coast on their left on the southern hemisphere, and they are trapped in the middle. They are trapped along the equator. Okay. So obviously, something is happening in the atmosphere and in the ocean along the west coast of the Pacific, which then the signal which is then brought to the western coast. And this is how El Nino signal is transferred from the western part or to the eastern part of the Pacific. And so knowing this, all these things, in order to approach experimentally the El Nino, we want any observationally we should develop a measurement methods or measurement pattern of experimental studies in a way that we are concentrated along the equator, and that we do measure along the equator and find out the progression of the signal which is formed presumably at the western coast of the equator, and then progresses eastward. And this is how really it does, how we do it. And we know that the velocity of these equatorial Kelvin waves, they are on the order of 2 meters per second. We more or less can calculate and find out if this is 5,000 kilometers. 5,000 kilometers is 5 million meter. If you divide this by 2, it's 2.5 million seconds. 2.5 million seconds. What is in terms of days? Do you have some? 2.5 million divided by 86,000, there are 100,000. 100,000, 2.5 million, so it's 250 days, more or less. So we can see, and we can understand, or we can from this simple consideration we find out that the more or less the El Nino signal, which is formed here on the western part, arrives about 1 year later. Okay, is it 1 year? 250? About 1 year, yeah. So this is that's if and to what extent theory and theoretical solutions of Kelvin waves agrees with the reality. We can predict within 1 year before we can predict the arrival of the El Nino signal, and indeed this is what has been done. There are a series of buoys, oceanographic buoys, which do several number of measurements like temperature, salinity, velocity, current velocity, and so forth. You can see how rich is this observing system with number of buoys here, which send the data in real time to the center where they do the calculations. This is obviously the international program. And this also can be used as an input for the numerical models in order to predict not only the time when the signal arrives, but also the intensity of the signal, whether the El Nino will be strong or not, and so forth. So, and this simple but rich measurement network is based on our knowledge of the Kelvin waves, of the equatorial Kelvin waves, on the way how this signal progresses, and what is the velocity of this signal which progresses eastward. So this is one of the applications, direct applications of the wave-like solutions of the equations of motions. You can also do the you can also do the estimates of the velocity of the coastal Kelvin waves. How do you do that? This is a very simple network of tide gauges. Tide gauges are the instruments which measure the sea level variations, and if you put these tide gauges along the coast in this way, as it is here, this is the South America coast. So this is the Chile Peru coast, and you have a number of tide gauges, number of measurements along the coast, and you can calculate the velocity of the signal, and these are the lag in days of the records between different tide gauges. So you simply do the cross correlation between those stations. You obtain the time lag, and then you can plot this thing, and you obtain the velocity. So you obtain simply the velocity of the coastal Kelvin waves by doing this simple time gauge measurements. Simple is a relative term, because the tide gauge needs a lot of maintenance and so forth. But this is something what we will talk about it. So, and here is the evidence of Kelvin waves along the coast of South Peru, and this you can see that the coast, the shelf is very narrow, and very steep. So the changes by small movements of the water column perpendicular to the isobaths can create the rather large changes in the vorticity, and also which means then a rather strong amplitude and quite important and easily evident amplitude of the sea level variations. And so this is why, obviously, in order to obtain the signal, you have to filter out the short time scale, the short oscillations, so mainly the tides. The tides are, the tides are pretty easily eliminated, because they are sinusoidal, they are harmonic functions. So you do the elimination of tides very simple, and what you are left with is, and tides are having the amplitudes much larger than the sea level oscillation due to the Kelvin waves. So you have to take care that you eliminate very good high precision the tides. Otherwise, the high frequency, that means the high tidal flow, can overlap, can cover the signal associated with Kelvin waves, because the Kelvin waves are the long-term changes of the sea level. And see so the data were low-pass filtered to eliminate tides and other variations with periods less than 1 day. What they do then the filter data from different stations were then compared with each other using cross-correlation, and that's a very simple statistical method. And it was found that each data compared best with the time series from different stations were shifted, lagged against each other in time, right? And so you can see this right diagram shows the lags obtained for the best, so for the highest correlation, and you can see which is relative to the northernmost station. Why relative to the northernmost station? Because the waves first passes to the northernmost station and then goes southward, And here, as you can see, the regular increase of the line for the highest correlation indicates that the variation of the current speed observed at this station travels southward along the coast with the speed. This is important. You can see the speed is 200 kilometers per day, which is 200 kilometers per day divided by 24 is around 10 kilometers per hour, and another division divided by 4,000 is well, 200 kilometers per day. So so you obtain this. Here they obtain also the speed of these Kelvin waves. You can go back into the equation and find out what are the other parameters which determine the velocity of these waves. And not only that, but you can also calculate how far from the coast these waves are felt, how far away these waves appear. Okay, so this is as far as as Kelvin waves are concerned, and they are, as I told you before, they are as I told you, they are associated to this. They are inertial gravity waves because they are a combination of the gravity and inertial forces, and they appear on an F plane where we can assume the constant F. There is another type of waves which are also very important, especially important both in the atmosphere and in the ocean, which transfer the signal over the ocean and sometimes interplay with the Kelvin waves in an ocean, in transferring the energy, transferring interacting also with the mean circulation of the ocean, which are the Rossby waves. So Rossby waves. And the phenomena which generates the Rossby waves are the differences in a Coriolis parameters between different latitudes. So here we cannot assume anymore F equal constant, but we should we should let the F changes with latitude. So we introduce in a Taylor we expect practically F is equal F0 plus beta, where beta is equal dF dy. So in the first approximation we assume the variability of the F, north-south variability of F as a value of F at a certain latitude plus its variability north-south. Okay, so this is just that we kept the first term of the Taylor development of the Coriolis parameter, and so we should take into consideration these changes of the Coriolis parameter, which again, starting from, I already showed you this thing, starting from the simple physical concepts. If you have a particle staying here at a certain latitude, if this particle for some reason has been moved northward, its relative vorticity it appears in an ambient vorticity where it has a vorticity smaller than the ambient vorticity, and so it has to move southward in order to go back. Once the force which moved this particle northward stepped. And when this force which moved the particle from the certain latitude where it stays, where it is in equilibrium as far as the vorticity is concerned with the ambient vorticity, once it moves northward or southward, it has to, if there is no force anymore which takes it far away from its equilibrium position, it tries to go back. So this is, for example, this one here. It moves here, but then it wants to go back, or vice versa, whatever you, for example, here. You go from here to here, it should go back, but it overpasses its equilibrium position, goes a little bit to the south, and then tries to go back. So there's in absence of the force which keeps this particle in an ambient vorticity different than its relative vorticity, this particle moves back and forth. And this is the mechanism how we explain, how we describe the Rossby radius for the Rossby wave formations. Okay, so they are different from the Kelvin waves. They are simply they are simply due to the changes, north-south changes of the Coriolis parameter. And let's see some description, some characteristics of staying at the qualitative part, some consideration about the oceanic and atmospheric Rossby waves, and they are known also as the planetary waves. For example, one of the very important manifestation of planetary or Rossby waves is those waves which appear along the polar front in the atmosphere. So what they do, they do travel westward. They travel westward. They do travel westward or eastward, and they travel westward direction. And they go around this polar front, so they travel as a perturbation on this polar front, which finally what happens is then their amplitudes in a certain moment increases a lot, and then there becomes instability. Then there is a formation of the polar cyclones and anticyclones which then travel and comes also to this area here. So they are important from that point of view. But anyhow, they are in the atmosphere. In the ocean, they come in different sizes and shapes. They are slow-moving. Rossby waves are fundamentally different from ocean surface waves. Ocean surface waves are those where the gravity force plays the important role. Here, as the important role is played by the vorticity. Okay. And unlike the Rossby waves are huge undulating movement of the ocean that stretch horizontally across the planet for hundreds of kilometers. So they have very long wavelength. And they are moving in a westward direction. Then, so that means that in contrast to the Kelvin waves that transport the signal from the east to the west. And the Kelvin waves are taking the signal from east to the west of the ocean. They are so large and massive that they can change Earth climate conditions, because they can bring the cold water or hot, warm water in different parts of the ocean, changing the climate over that area. And then they cause the rising sea level, and then the effect of El Nino. So they take part also in El Nino events, transferring this signal eastward, northward, and their movement is obviously complex, and the horizontal wave speed of a Rossby is dependent upon the latitude of the waves. You will see, and I would invite you, one of you who wants to show us, to make a 5 or 10 minutes presentation of the solution of the Rossby wave solution, who is volunteer in this so that we can have this. I promise I won't ask you anything except of that. So you just present the five slides and explain to us how to obtain the analytical solution which represents Kelvin wave. It's not a very difficult. It's not a very difficult exercise, and if you would like to do, and it will be better for you and better for me. So I don't know. So whatever. If there is a volunteer, I won't tell you anything about the solution. If there is no, I will do it for you. And so this is from the equations. Looking at the solution, we can see that their speed or the velocity is a function of the latitude, and waves at lower latitude, closer to the equator, may take months to years to cross the ocean. So they are very slow but very, very large. Waves at the farther away from the equator of the Pacific may closer to 10 to 20 years to make the journey. The vertical motion of Rossby waves is small along the ocean surface and large along the deep thermocline. Here is another thing what we should mention, which is general, which is something which is important not only for the Rossby waves, but also for any type of the deformation of the free surface, and comparison between the deformation of the free surface and interfaces. Interfaces in terms of the isopycnals or isotherms. Here it says that the perturbation at the surface are much smaller than the perturbation in the interface. This is like saying that if we have, you remember we were talking about this shape of the sea surface due to the convergence induced by the wind. So that means that the wind generates the convergence this way. So we have, and as a result of that, we have the vertical motion, downward vertical motion. As a consequence of that, the shape of the isopycnals is this way. Okay? This is that's vice versa. If you have the divergence, then you have the sea surface has a dip, and then the isopycnals are formed in that way. What is important here to know, to take into consideration, that the order of magnitude of deformation of the interfaces is much larger than the deformation of the free surface. Free surface on 100 kilometers can be on the order of 10 centimeters. This is a typical sea surface deformation, unless we talk about extremely strong currents in Gulf Stream, when we have on 100 kilometers we have 1 meter. But this is the case where we have a very strong current. So we have a 10 centimeter deformation at the free surface. But if you go deep and find out what is the equivalent deformation of the interface, you end up with the numbers like on the order of 100 meters. Okay, so instead of 10 centimeters, we have 100 meter deformation at interfaces. And this you always have to take into consideration. For example, in India Ionian, when we do these measurements, we obtained the sea surface deformation by satellite altimetry. And by doing at the same time doing the transect by ship, we were able to obtain the cross section along the bump in the sea surface, and we were able to calculate these deformations of the interface which are equivalent to this kind of deformation of the sea surface. And we end up with these numbers. Okay. And the same thing happens for all the motions in the ocean. Kelvin waves, internal Rossby waves, the influence of the wind, or convergence, divergence. Always we have several orders of magnitude larger deformation in the sea surface than at the interfaces. And in fact, what it says here, and that the vertical motion of Rossby waves is small along the ocean surface and large in deeper thermocline, and the variation in vertical motion of the water surface can be quite dramatic. The typical vertical movement of water surface is generally 4 inches or less. 4 inch, 1 inch is how much? 1 inch is 3-4 centimeters, few centimeters. And while the vertical movement of the thermocline for the same wave is approximately 1,000 times greater. This is what it really says here. Here we have 10,000 centimeters with respect to the 10 centimeters. So we have the 3 orders of magnitude larger interface moment than the sea surface moment. In other words, for a few centimeters or less surface displacement along the ocean surface, there may be more than whatever, 1,000 meters or corresponding vertical movement in the thermocline below the surface. In fact, due to this very small deformation of the sea surface, the Rossby waves cannot be detected by direct measurements. But what is important is that although the quite few centimeters on 1,000 meters, the horizontal distances, due to the recent reached precision of the satellite altimetric measurements, we can also detect these waves, also looking at the free surface deformation. So it's not, they are at the limit of the precision, however, we are able to detect them. Okay, so I expect the volunteer, and when expecting the volunteer, we can go ahead. So these are the Rossby waves. There are 2 solutions, and let's see what. Before we pass to the instrumentation, I would like to go back a little bit and try to connect, try to see how do we connect the wind stress with the average circulation, because the average oceanic circulation is something what has 2 main motors, 2 main mechanisms which are keeping it going on. One is the differences in temperature and salinity, or mainly temperature between the polar and equatorial area, which is a thermohaline circulation. The thermohaline component of the world ocean mean circulation. And the other one is the wind-induced long-term circulation of the world ocean. These 2, when you put them together, they are making the circulation they're making the circulation 2-dimensional, because otherwise, if you think about thermohaline circulation, it will be 2-dimensional. It will go, it will be north-south and in a vertical. If we are talking about the wind influence, then we have a 3-dimensional circulation. We have horizontally asymmetric, horizontally evolved, and in the vertical as well. So it's partly due. So the combination of these 2 makes the circulation. Therefore, apart from these differences in LC heat fluxes, or the differences in the differential heating of the polar and equatorial areas, we can look at the global surface wind stress and curl in order to obtain where we have the areas where we have the convergence and divergence and the vertical movement associated to the convergent or to the vorticity in the wind field. And this is the wind stress, what we have mentioned and discussed a lot last lectures, where you can see this is the annual mean, and you can see that there are areas where we have easterlies and westerlies between themselves, what we have shown very schematically in our previous lectures. And here is wind stress curve. Why do we calculate the wind stress curve? We do calculate wind stress curve because this is how this three-dimensional flow is driven by the wind. So we have it, and here you can see the negative wind stress curve are those areas here in subtropical areas. Wind stress curve is negative, and we have a positive wind stress curve in an area where we have the easterlies and westerlies one close to another. And then finally we have here the negative wind stress curve along the equator. And so this is that's what we have seen before in a very schematic way, but we can see here that the situation, real life situation, really is very similar to what we have learned in a schematized way. Then certainly the wind stress curve negative corresponds to the anticyclone, and wind stress curve positive corresponds to wind stress cyclone. Sorry, to the ocean cyclone, cyclonic gyre, an anticyclonic gyre, and this superimposed on a thermohaline circulation gives the way in which the heat is transported from the equatorial area toward the polar areas, and due to the and then you have here the closed circulation because of the continuity equation, or the northward flow has to be compensated by southward flow in some part of the ocean. We have talked about it a lot about this in westward intensification. And this is the asymmetry what we have talked plenty of times. And here is the Deokman pumping associated to this wind stress curve. Deokman pumping, which is the negative, are bluish areas, and here is the reddish area or yellowish area are those the Deokman Saki. And again, we see that the Deokman pumping corresponds to the anticyclonic vorticity. To the cyclonic vorticity, we have the Deokman suction, and here you have along these areas correspond very well one to another. And here is the description of the legend of this figure. And so you see also from the Deokman pumping pattern, you can see the anticyclonic or cyclonic circulation, or cyclonic or anticyclonic gyres. This is This is the Sweater balance. I won't talk to you anymore because we have passed through this thing here. Again, one more going back to this pattern where we have the Deokman transport in the surface Ekman layer. We have the thermocline. We have to keep in mind this thing here. The formation of the thermocline is much larger than the deformation of the free surface. This thing and this thing are 1,000 times, three orders of magnitude different as far as the vertical amplitude is concerned. And we have another thing. What is important to see is that you have the horizontal shear, the shear of the vertical of the velocity, and here you have. So you can see in the interior you have this shear, and you have here the Deokman transport, which is the largest in the center of the anticyclonic jar. And this is just to give you the potential vorticity review from the previous lecture. We have again potential vorticity is planetary plus relative vorticity plus divided by column height. This is the concept is that what we have seen before in a Kelvin wave type of solution, where we have only the relative vorticity divided by h, divided by the height of the water column. If you talk about the large scale motions, then we have to keep in the consideration f plus h, and then we have a relative planetary vorticity and the stretching due to the fluid column stretching. This stretching or squeezing appears not only on the long term, on the average flow, but it appears also at wave-like solutions, what has been seen in a Kelvin wave solution, what we have seen a few minutes ago. The Deokman transport, how it drives the underlying circulation, because if there is Deokman convergence pumping downward, then h decreases, and this must result in a decrease of a numerator f plus theta, and then this thing here has to be conserved. So if there is a decrease in h, there should be a decrease in latitude as well. So this is how the particles are moving, always keeping keeping this term constant, and so the Sweater transport is the meridional flow due to the Deokman pumping and Deokman suction. If you want, for example, to understand back on an envelope back on envelope calculations, what is the pattern of the mean flow over the ocean, how will we do it? We will simply calculate f over h. So isolines of f over h would be the lines of streamlines where the flow goes, because the flow in a steady state should follow f over h isolines. So if you plot simply the f over h isolines, you know that your flow will go parallel to these lines, because of the fact that f over h has to be conserved. So because of the expression that dt f over h is equal to 0, or f over h is equal constant along the lines where the flow goes. So this is what we have seen before, that if we have a bump at the bottom, when the water column comes to the bottom, and which is shallower, then it has to turn southward in order to maintain this F over H constant. Okay, because F becomes H becomes smaller, and then F have to become smaller too, and then the particle will, for that reason, the particle will go southward. So that's a very simple example of the fact that we have to keep F over H constant along the
Excuse me, Professor.
Yes.
You go back to the slide.
Which one? This one? Yes.
Yes, I don't understand why, if there is Ekman convergence, then H decreases. Because if we take for H the thickness of the surface layer, we should have it increased.
If we have a convergence, then we have the, yes, that's wrong.
So in that case, H
That's wrong.
is the depth of the surface layer.
Right.
The layer which is
No, it has to deepen. Yeah, that's wrong. That's wrong. Yes. You're right. Good point. Okay, let's skip over these things.
Excuse me.
Yes.
Can I volunteer to do the analytical solution doctorally?
You want to do it?
Because the first part was really short.
You're very short.
Yeah.
Okay.
So I do the first one.
So you want to give somebody else the?
No, do the first one.
You want to do both?
Yeah, the first one is really short.
Both. Okay. You do both? Okay. So you lost the Rossby wave solution. It's John. You're John, right? Yeah. John took everything. So I have to play a few other things by Friday, and I'll give it to you. If you are interested. If you aren't interested, we can do the classical exam if you want. What do you want? Classical exam? I ask you everything, or you tell me something?
I'll tell you something.
You tell me something. Okay. So this is the Ekman upwelling downwelling map, which comes from the convergence divergence map, and here is the same pattern, and the blue regions is Ekman pumping. Ekman pumping means that the water column stretches, so there is a southward flow, equatorial sweater flow, or if our yellow or reddish areas, there is an Ekman suction, so there is squeezing of the water column, and there is a poleward sweater transport because of the theta plus F divided by H is equal constant. If you assume that H is constant, then theta plus F has to be constant. So that means if we sorry, it's not true. If we increase if we stretch the water column, we increase the positive vorticity, and thus the water column has to go southward, equatorward, and vice versa for the Ekman suction. Squeezing of the water column, the water column has to move northward in order to maintain the potential vorticity constant. So that's what we obtained looking at the upwelling downwelling map due to the wind influence. Here is a thread of transport in the Pacific, and these are the things what we already seen many times. And if we go and look at this is a part of this general circulation. This is the ghost stream what I have shown you already before. This thing was a number of eddies and gyres, and takes this warm water So this is the this is part of the wind-driven subtropical gyre, and at the same time is driven by the thermohaline forcing, because it brings the heat to the north. So in the surface, it is also an expression of wind influence and the thermohaline forcing. This is an old map in a few centuries ago, which shows how they imagined the Gulf Stream at that time, because the Gulf Stream is so strong that it was recorded simply during the passage of the ships, because 1 meter per second is really felt in a navigation. And Franklin, I think, we have seen before in this historical overview. Franklin, he was mapping the Gulf Stream by looking at the drifting of the post ship would bring the post to the United States to their drifting due to the Gulf Stream, and he did this kind of map for the Gulf Stream. So these are the first observations, not directly organized by oceanographer, of the strong current in the ocean, which then has been developed as a part of the These are the one more thing, and then we will stop here. And next time we'll start with the instrumentation. This is the swelltop transport. Generally underestimate subtropical gyres where there is no this circulation governed by the wind influence only, and you can see these are the transports which are associated with these currents. So here we have here is a Florida current, which is about 30 million meter cubic per second. Here's the flow. Here it reaches 60 million meter cubic per second, because there is entrainment of the surrounding waters, so it becomes larger and larger. And finally here is about 150 million meter cubic per second. It's a huge amount of water which is brought to the north. And these as I told you before, the estimates of this flow here is rather simple by doing the measurements across the jet stream, across jet flow. And swelltop transport is not really, doesn't explain everything, because it's only one approximation, but describes main features, and it suggests, for example, the strong zonal flow of the Southern Ocean. But it's not observed. There is a Goldhus current from Indian Ocean which goes to South America, but this is very turbulent flow, where you have a lot of eddies which are formed, and from there they started this consideration that eddies can be considered as black holes in the ocean. By studying these eddies which are formed, they are Goldhus current in the southern tip of Africa. That's it. Okay, so we are more or less now at the end. I hope I succeeded to transfer your message that very often the interplay between theory and some simple analytical solution and simple experimental approach can give a very nice nice results and nice explanations on what is happening in the ocean. I will, if I will have time, I will show you a few examples of our studies here in the Ionian, which use different concepts of the oceanography, which gives very nice results, and I might give you 1 hour lecture about that, so that you can enjoy as I enjoyed. Okay, good. Thank you, and see you on